you know, the way I wrote, maybe somewhat like that, and you have to really see. So basically the question is this, that you are starting at 1,0, but let's not draw coordinates because it will get really, because of the jump of 10. So you can go from x comma y to x minus 1 and y plus 10. Okay, or you can go maybe like, you know, x plus 10 and maybe a little down. Yeah, x plus 10 and y like this. Yeah, x plus 10 and y minus 1, right? And in this way we are saying that you can never reach the line y equal to x. Yeah, so you can never reach any k comma k. Yeah, in this way you want to say, and you're starting with 1,0. Yeah, so show that both coordinates cannot be made same. Yeah, and it's quite believable if you try a little bit. Like here you can do this, and here there's only one option. You can make 10 9. Right, is it? Yeah. Wait, so okay, you can do this, and similarly now from here you have options, so you can make like 20,8. Okay, or you can make 9,19, and again you have two options, and you can see that the coordinates don't seem to become the same. Yeah, it seems like you cannot make them the same. Or you can make 19,18, so almost same but not same. And here also you can see it becomes 8,29, or you can make so this is like, you see, this is interesting thing, 19,18. Yeah, but it doesn't seem to become same. How do we prove such a thing? So what you really have to find is find an invariant. You have to find something that is not changing, or just to put it, there is some pattern in these changes. That's what a pattern means, right? Finding an invariant is what finding a pattern means. Same thing. Something that is not changing. Some pattern rather is better. So like something that x and y, that always distinguishes x and y. Initially they are distinct, right? And something that just maintains that. The sum on each level of the tree is the same. Yeah, that is an interesting observation. Yes. So I have not really drawn it properly, but you can see that this sum and this sum is the same. Right. 10 9. Sorry, so from here, So that's what I've written, or is it? Um, but for that he has to make another exchange, right, to go to 28. Yeah. So it's a binary. So okay, it's not a binary tree, but yeah, at each stage there are two branches. But as you can see, it's kind of there is a kind of not, it's not a cycle, but whatever. Yeah, there is a. So after k exchange, after any number of exchanges, the total amount that he has is a constant, right? That may not be useful to solve the problem, but that's a good observation. Yeah, I think after k exchanges, sum is, so what should the sum be if it's a constant? Uh, it is increasing by, so what is it increasing by? It's increasing by 9, right? So after k exchanges, it should be 9k plus 1. Is that, yeah, at least you guys can see the pattern, right? Yeah. So does everybody see this? And it's easy to prove, don't worry about that. But if you just see the pattern, means don't go for proving, but you can see the pattern, you see. At here it is 10. Obviously at the next stage, it's no matter what you do, okay, here you can see just it's increasing by 9. But the next stage, I mean, one of them is decreasing by 1, the other is increasing by 10. So obviously increasing by 9, and it doesn't matter for, so it's always, this is a good one. But this doesn't help you to solve this question because you see this 9k plus 1 could be an even number, right? And an even number could be split into two equal parts. But you see, it cannot be. So we need something more. Okay. We need something more. That's, so how about you try to calculate the difference? Yeah, because it's about equality, right? So rather, other than the sum, try to focus on the difference between the two coordinates. That could be a, how does the difference, how does the difference between the two coordinates behave? So focus on the difference. I mean, that's the idea that comes to my mind. Focus on the difference between the coordinates. In between x coordinate or y coordinate or something like that. Right? So here you see the difference is 1, and here you see the difference is minus 10, and then again the difference is 1. Here the difference is 12. Here it is minus 10. Here it is 13. Here it is 1. Okay, wait, what? It's not 13. It's 23. Uh, how much is 25 minus 8? 17? Minus 17? Sorry? That's what I was thinking. That's why I was getting confused because it's not coming what I thought. Okay, that's why I couldn't subtract properly. I'm not willing to accept the subtraction that I made. So 29 minus 8 is 21. Yeah, that's minus 21, let's say. These numbers are peculiar. These numbers are not arbitrary. There is something in these numbers. Okay, that's uh, okay. There is one, but I don't know if that will always hold. Parity is alternating. Okay. We need to say a little more than parity, where parity will not be enough here. So, I mean, if you want to think more clean, like if you don't like this, what I'm saying, in the sense you can think more like a nobly from here itself, x minus y and what happens to x minus y in the next step. If you're not the kind of person who wants to think too much like numbers. This x minus y here, you look at what happens to x minus y here. Here it becomes x minus y minus 11. Okay. And here, what is the difference? X minus y plus 11. Yeah. It's increasing or decreasing, but there is. But something is not changing. If x minus y, so focus on the differences, right? X minus y is becoming x minus y minus 11 or x minus y plus 11. And we are in the topic of, so okay, that's okay. Let's forget about that. Let's just think, yeah, because that's not useful. But yes, if x minus y was not divisible by 11 initially, then it will never become divisible by 11. Good. That is the thing. If it was initially not divisible by 11, then it will never be divisible by 11. Because you can see what is happening, right? X minus y is becoming x minus y minus 11 or x minus y plus 7. If the difference initially was x minus y or at any stage is x minus y, then it becomes these two things. What does it mean? It means that the difference, it's proper. What is it, up to remainders by the number 11 does not change. Yeah. If x minus y was not divisible by, simply put, if x minus y was not divisible by 11, then at the next step also they cannot become divisible by 11, right? If 11 does not divide x minus y, then how can 11 divide x minus y minus 11? That is impossible, right? Same thing. So it will not divide, and so it will not divide here also. And then see, because it's not changing, we have found, so always you have to focus on a small step. I mean, pattern is seeing, but then abstractly you're right. So this is how I have done many times kind of questions. You see a pattern, but then if you can see vaguely, right? Or then you can try to see it in a abstract. So when you want to analyze the one step thing, maybe see it abstractly. Yeah, like variables. And you want to analyze many, if you want to just see numbers, then many are obviously needed. Anyways, that's not. So you see, this is the point, that if at some stage it is not divisible by 11, the difference is not divisible by 11, then at the next stage also it will not be divisible by 11. But then this thing will continue. This is the nature of the statement. It's an invariant. That's the magic of invariance, right? Something doesn't change, it doesn't change. So at the next step also, it could become something more complicated, though it's not becoming very complicated. I mean, again, it will either become x minus y, and it will become both. You can get both, right? It will become x minus y minus 11 minus 11, or you can get x minus y back by adding 11, right? Or from here also, you can get this, or you can get x minus y plus 22. Okay. You see, so more interesting questions can be made out of this. So maybe one is coming in the test. Okay, maybe, but let's not say it now. But this is the thing. You see, it's always the same, not changing modulo 11. And yeah, okay, cool. And then from here you can see that parity thing also will be clear from here, and you can see. So anyways, so and initially it is not divisible by 11. Initially the difference is 1, and so it will remain 1. Okay, all right. So it's not simple, but not very difficult also. But there are several steps in this problem, and obviously you don't have to follow. I mean, I'm just saying that there are several layers to this question. Okay, first understand the question, and then maybe if you need to write it abstractly, little like this, like okay, what is really happening? Okay, 10 comma 1 is becoming this. So you write it in a simple way, mathematical way, as I'm saying, and then you can analyze things more faster. And both these things are needed. And numerically, you have to write, and also sometimes you have to write it in the variables. Both you have to, both will help you. Okay, so we took really long to do this column, but okay, because I got stuck in the beginning. So just say, see if there are any questions, and then I'll move to the next one. Today it's a little off. I don't know, taking a long time to do these things. Let's try to do the next one. So this is going to be problem 18 from mathematical circles, and this is going to be this. So again, there is a person, so Dr. Gizmo, he has invented a coin changing machine which can be used in any country in the world. No matter what the system of coinage, the machine takes any coin, so this is the key, takes any coin, and if possible returns exactly 5 others with the same total value. Okay, with the same total value. So basically, like if you put in a 10 rupee coin, yeah, let's think about in the Indian system, right? 10 rupee coin, then it will return you, the machine will return 5 coins, yeah, which will add up to 10. Like you can just say maybe 5 twos, or 1 5 and 2 twos and 1 whatever 1 1, yeah, the coins that exist. So let's say 3 rupee coin does not exist, so we then that's, yeah. So then for example, if you enter the rupee 6, okay, if you enter the rupee, if you enter I mean, if you enter some coin which cannot be broken into 5 equal parts, into 5 parts, not 5, into 5 parts, then will not return you anything. Okay, so the question is, I'm write the question, but to prove that no matter how the coinage system works, okay, in a given country, you can never start with a single coin and end up with 26 coins. Okay, this is a strange question, interesting question. Yeah, so there is a machine M, okay, takes in a coin, maybe I should say of value, yeah, so I'll just say coin of value X, say, okay, and returns, if possible, okay, returns if possible, because you see it may not be possible to break a coin into give 5 coins in that currency which add up to it, right? If possible, returns 5 coins, may or may not be different, with total value X. I mean, yeah, it's just split, coin splitting machine, okay, change making machine, yeah, with total value X. Okay, so what I'm saying is just that the X becomes A1 plus A2 plus A3 plus A4 plus A5, if it is possible. Okay, so just so again, before we move forward, can anyone give so let's stick with the Indian system. We know what coins are available, standard, okay, let's say 1 2 5 and 10, yeah, this is standard. So in the Indian system, can you tell me some coin of it? Some not coin. So it's just, is it just coins that it's splitting? Very strange. A machine will, if you enter any coin, it is that's very strange. No, that's not true. That's not equal value. Yeah, but so, and any system, I mean that system, let's say that if a system has a 13 rupees, so let's say that if the Indian system had a 13 rupee coin, okay, then could you break it into 5 coins of the other standard ones? Standard coins. Yeah, so yeah, this can be done. Just take 55111, right? These are standard coins. Yeah. So 13 can be done, but yeah, so there'll be some number maybe which cannot be done or whatever. Yeah, that's not, yeah, that's fine. But now the question is not just about the Indian system, but the point is that start with, so we are starting with, are we starting with, so no matter what, no matter how the coinage system works in a given country, you can never start with a single coin and end up with 26 coins, okay? So that's all we want to show, okay? Show that we can never get 26 coins, whatever values, that's not the point, but just 26 coins from a single coin. Any value, the value is not important. We are showing that, we are trying to say that no matter what your initial value is, and no matter what standard coins are available to you, you can never go from 1 coin to 26 coins. Right? Like what I'm just saying is, initially, what can you do? You can go from 1 coin to 5 coins, right? And then what can you do? You can, in this 5 coins, you can put one of them in the machine, right? And then, so 4 of them will be just there, and that one will become 5, right? So it will become 9 coins. But you could have done many things, right? You could have put 2 of them in the machine, and so it will becomes 5 minus 3, and those 2 will give you 5, 5. So that becomes 10. And so you get these many coins, 12 coins. Yeah. So there are several ways to, to get different numbers of coins. Let's say right here. So the exact value is not important. And many other things you could do. And you're allowed to take as many steps as you want. But the claim is you can never get the number 26 here. That's all. That's all we are asking. Okay. So just make sure you have understood the question and then try to solve it. So let me know if yeah. That is right. Yeah. So you cannot split all. Yeah, that's right. That's right. That's right. So, I mean, even some other coins you may not be able to split, right? So if one of the coins here is 1 and the other is 2, and let's say another 1, another 5, and another some 50 rupee coin. Yes, then you cannot break this one. So what yeah, so you cannot break this one, what does that mean? It means that you cannot break more than 3 coins, right? So you can break one of the coins, you can break 2, for example, and then you are going to get how many coins? I'm just going to write you're going to break 1 coins, then you get 4 coins first because you remove 1 coin for breaking, and then 4 plus 5, so you get 9. Or as I said, you can get 12, or you can take 2 plus 15, 17. Right? So these are the things you can get, but you cannot break 4 coins because there are 2 ones, right? So you cannot break 4 coins. So what you cannot get if this was the situation is 5 minus 4, 1 plus 4, 20, 21. You cannot get 21. Okay. So yeah, that way it becomes a little complicated if you are actually going into what exactly you can get. Okay. But I am still going to say, in some case you can get 21, right? Yeah. In some cases you can get 21. So the point is that certainly you cannot get anything outside these and 25 if you are willing to break all the coins, if you can. I mean, the point is that outside these you cannot certainly go. Is that right? After 2 steps, yeah. You certainly, certainly cannot get outside these numbers, in these many steps. So, okay. We need to show that you cannot, sometimes you cannot get these also. Like if all of them are 1 rupee coins, then you cannot move at all. But even if you allow everything, still you want to show. That's why we're saying in any coinage system, in any coin you start with and so on, you cannot get the number 26. Okay, you cannot get the number 26. What is it about the number 26 that you cannot get? Yeah, and this is wrong. This will be 13, right? Not 12. Okay. Right, that's correct. All of them are odd. So can you show that you will always have odd number of coins? So what is happening if you have X coins? Yeah, let me write this a little separately. Yeah. That's it. Yeah, they're always increasing by a multiple of 4. So you subtract 1 and you add 5. So what are you doing? You're adding a 4, basically. You can see that there also, but or if you subtract 2, but you add a 10. So again, you're increasing by 8. And I mean, it's clear, but yeah. Yes, exactly. And X plus 16. So you can always increase only by these things, 4, 8, 12, or 16, and multiples of 4. So the number will always remain odd. The number that you get will always remain odd. Okay, so that is what it is. Yeah, and you can also try to show that you cannot, or I mean, can you get? You can think, can you get the number 27? It is odd, but I'm trying to say there's more to just odd. Being odd and even, there is more to this than just being odd and even. You can already see by increases by 4, not by 2. a multiple of 4. But you can think about this. Yeah. So let's keep that for homework. It's good. You can build on this. Okay. Yeah. So then try to do the other problems. So the problem with these questions is a slightly verb, like a lot of words are there. So you have to break it down. You cannot help it. Yeah. Okay, and you can read the comments here. Some interesting comments are there. You can see, but really try these problems. And brilliant. I hope you guys have tried. I mean, if you're not trying, then do it. And ask me between the classes and so on, because now there'll be some gap from Wednesday to Monday. So you can see. Okay. Maybe in the next batch, when I split, maybe one batch, I can try to do 3 classes or something like that. Okay. As I see. But right now, I feel there is enough to try, and you have to be in that sense, more and more self-sufficient. Okay. And think on your own way. Yeah. Okay. So I think let's stop a little early today. Let's stop this today on time. And yeah. So, okay then. Thank you.